Okay, so we've gone through some examples, real life examples of hydrated ionic compounds. So now let's take a look at how we can determine how much water is trapped in the crystal lattice when we have these types of compounds. Okay, so quick little recap. When we're looking at all of these, they are ionic compounds, which means they're compounds composed of ions. Over here, I've got this nice little visual of a crystal lattice. So again, you can imagine, let's simplify this. Think of it as sodium and chloride. For every one sodium, you have one chloride ion. And what's holding all of these little ions together, holding it in these clusters, are really, really strong electrostatic forces. That means there's attraction between the positive cations and the negative anions. Now, when we have structures that form a crystal lattice, we can break that lattice apart oftentimes by placing it into water. So sodium chloride, its crystal structure, here it is when it's in its solid state. And if you recall from our first unit, when we go to dissolve salt, and we know table salt dissolves, we'll find that all of the negative ions end up becoming surrounded by the partial positive charges on the water molecules. Sorry for the pause. The positive cations, similarly, they end up being surrounded or hydrated by water, but when they dissolve, the partial negative charges on water, on its oxygen, will surround the cations. Okay, so we know ionic compounds, most of them are pretty attracted to water, and if they are more attracted to water than the ions are to one another, then the substance will dissolve. Now, when we look at hydrated ionic compounds, it doesn't simply mean it's like an ionic compound you put in water and it dissolves. What a hydrated compound is, it's an ionic compound that within the crystal lattice itself, we have a bunch of water molecules trapped. So our example here of Epsom salts, these are salts, ionic compounds comprised of magnesium sulfate. So here's my magnesium ion, Mg2+, and here's my sulfate ion. These magnesium sulfates oftentimes will form a lattice with about 7 molecules of water that get kind of trapped within the lattice itself. So in those spaces where the cations and anions attract to one another, sometimes we get water stuck in it. So that's termed a hydrated compound. If it's dry quotation marks, the dry form without water trapped in the crystal lattice itself, we say that it's an anhydrous compound. Whereas if there is water, it's a hydrated compound. Now, both of these, whether it's dry or the hydrated form, we would find in the solid state. So if you get a bag of Epsom salts, so you take these, if you have a particularly hard workout, you want a nice relaxing bath and allow some magnesium and sulfate to soak into your muscles to help relax them. You get a bag of these Epsom salts, dump them into the tub, let them dissolve. But in that bag is this hydrated form of magnesium sulfate. Okay, another example, Glauber salts, which is a natural horse supplement. So for your horse health, all of your horsing needs, this is a compound that's comprised of sodium sulfate, and then it is surrounded by several water molecules that get trapped in the lattice. Okay, borax. If you can find a box of this, maybe somewhere in your laundry room. This is where we have sodium tetraborate. So here's my sodium ion, and then 4 borate ions all combined. That's the tetraborate anion. That would form a crystal lattice with a bunch of water molecules that get trapped within it. So all of these are examples of hydrated compounds. Even though we see them as solid, their natural state at standard temperature and pressure, it's in a solid form, there's water trapped in the lattice. Now, copper sulfate, if we get back into the lab next week, this is one that we can look at. And you guys actually played around with this in a few of our labs. This was that blue crystal. And actually, our very, very first lab we did the physical chemical change lab, we heated this. And then what we were doing when we heated it, we were driving off or kind of boiling off the water that was trapped in the lattice. So if you recall in that first lab, if you can go back and look at it, you had this very fine blue, kind of bright blue crystal. And then when you heated it, the color changed to white. And it was that color change occurred because we started to lose water from the crystal lattice. And then the second part of that lab activity, we added water, maybe a dropper full of water back in after it had cooled, and all of a sudden the blue color reappeared. So when it's in its hydrated form, this copper 2 sulfate, it's a pentahydrate. There's 5 waters trapped in these crystals for every 1 copper sulfate. It has a very distinct blue color. But if we are able to drive off the water, we have a much paler blue color. In some cases, you might even detect it like a really faint blue or white. So those are all examples of hydrated compounds. Now, if you flip over to the note or the handout, this is where we can fill in a little bit of information. So just some of the points we've talked about. So many ionic compounds will crystallize. They form their crystal lattice and water gets incorporated or trapped within the lattice. So we go to Epsom salts, magnesium sulfate, heptahydrate. That's our classic example. You might find some of them in the bathroom. Go around and look. When it's in its hydrated form, what you're going to notice with the formula is that for every 1 magnesium, I have 1 magnesium here, and 1 sulfate ion, there's 7 waters that get incorporated or trapped in the lattice. So we represent that by putting the formula MgSO4, that's 1 magnesium and 1 sulfate, and then this little dot. I know sometimes for math you see that as multiplying. But what that little dot means here is that for every 1 of these, I didn't write the 1 in front, but I could have, there's 7 times as much water. Now, when I say there's 7 times as much water, I can kind of think of it this way. For every 1 mole of magnesium sulfate, there's going to be 7 moles of water trapped in the lattice. Or, on a really small scale, for every 1 magnesium sulfate formula unit, there'll be 7 molecules of water trapped in the lattice. I mentioned this before. If a compound has no H2O trapped within it, we say that it's anhydrous. Okay, so this would be my magnesium sulfate. You notice with the formula, it's completely dry, no water. And here's my hydrated form. Now, why this is significant, why this is important, particularly to chemists and biologists, we want to know exactly what the mass of our compound that we're working with, so we know that we have the correct proportions, particularly if they're going to undergo reactions. And that's what we're going to get to in our last part of this unit. So if I were to look at my hydrated form of the compound, in order to find its molar mass, I'm going to add up a magnesium, a sulfur, and 4 oxygen. Okay, and I've just shown this in grams per mole. And then I'm going to add the mass of 7 water molecules. So that 18.02, if you've been kind of practicing, that comes from 2 hydrogens and 1 oxygen. So when it's in its hydrated form, you can see that the molar mass, 246.52, is much, much larger than it is in the dry form. And that should make sense. It has extra water trapped in it, so of course it's going to be heavier. And that will play a significant role kind of in our last part of the unit. We want to make sure we know whether we're working with the dry form of a compound or the hydrated form. Okay, so we're going to go through a couple examples of things that you might be asked with hydrated compounds. So let's go through the first one that you've got on your note. Let's go with this example, a 50-gram sample of the barium hydroxide hydrate, BaOH2. There's barium hydroxide, contains 27.2 grams of barium hydroxide. That sounds weird for a second, doesn't it? But I've told you that this is the hydrate, which means there's water incorporated in the lattice. Now, the thing is, I don't know, and I haven't told you how many waters there are trapped in the lattice for every 1 formula unit of barium hydroxide. So for now, I'm going to represent the fact that this is a hydrate. Well, it's an unknown formula. I don't know how many waters. I'm going to put an X here to represent that unknown value. So two different types of questions you could be asked is let's A, calculate what is the percent of water in the hydrate, and B, can you calculate how many water molecules there are trapped in the lattice for every one formula unit of barium hydroxide? Or in other words, can we find out what X is? How many waters are stuck in the lattice for every one unit of barium hydroxide? Now, our first example, if we're finding the percent H2O, this is very much like a percent composition question. But just instead of breaking everything down into hydrogen, oxygen, into individual elements, what we're going to do is find out what percent is water and what percent is the ionic compound. So if I were to start with this first portion of the question, what I want to know is what is the mass of water in the compound? So here's the total sample was 50 grams. I know that 27.2 grams of this are barium hydroxide. Well, that must mean the rest of it, the difference, would be how much water there is. So I've shown my first calculation here. I found, well, what's the mass of water? So I've subtracted these two values. Now I want to know out of the entire 50 grams, what percentage is H2O? Again, sorry I didn't get my subscript there. So if you look back at this is like a percent composition or a mass percent question that we did a couple days ago. I'm going to take the mass of water divided by the total mass of the compound, and therefore 45.6% is H2O. And I've been careful of my significant digits again, 3 and 3, so I've rounded it to 3. Okay, I think that's pretty straightforward. We're just not breaking it down into individual elements. We're looking at the percent of water as a whole. Okay, now the second question was saying, okay, for every one barium hydroxide, how much water is trapped? And again, barium hydroxide and water, they have two very different molar masses. So what we're going to do, we're not going to compare the masses directly. We want to compare the amount in moles. Whenever we look at chemical formulas, we're comparing the amount in moles of each element. Now, this looks very similar, in fact, to an empirical formula calculation. But again, instead of breaking it down into barium and oxygen and hydrogen, what we're going to do, it's actually less work, we're going to find out how many moles we have of BaOH2, the ionic compound, and then how many moles we have of water. So I'm looking at the formula. I'm going to find out how many moles I have of this first portion and compared to how many moles of water are trapped in the lattice. So we're still using that formula, moles is mass divided by molar mass. I know the mass of my ionic compound when it was dry, without water, was 27.2 grams. I'm going to convert that to an amount in moles. And the way that I've done this, I'm using molar mass, barium hydroxide. I added up a barium, 2 oxygen, and 2 hydrogen to get my molar mass. And that tells me, or just helps me convert from a mass into a molar amount. Now notice here, I'm starting to use these little subscripts, very similar, so they're starting to, but similar to what we did with empirical formula. And that's going to help me identify, it really helps me keep straight in my mind what the molar mass is. What is the compound I'm looking for? So this is helping me identify what atoms I need to add up their molar masses to find. Okay, now I'm going to compare, one down, one to go, how many moles of water I have. So we found previously that the mass of water in my sample was 22.8. There it is. And we're just going to change this into a molar amount. And here we have it. So 1.265. Well, now what I have is a ratio. For every 0.1587 moles of barium hydroxide, I have 1.265 moles of water. But again, that is not the best looking ratio. I think we want to have it in nice whole number values. So in order to find X, that was how many moles of water we have, what we're going to do is just like we did for empirical formula, we're going to divide both of these numbers by the smaller of the two. Now, I don't really need to do that for barium hydroxide because it's going to be 1, But essentially what I'm doing is dividing both of them through by 0.1587. In order to find X, that's telling me how many moles of water. Here's my calculation. Moles of water, moles of ionic compound, and I find that it is very close to 8 times the amount. By comparing those two, I've solved for X and I've identified the type of hydrate I have. So this would be barium hydroxide. This dot should be a little higher up, I'm sorry. And in that compound, there's 8 H2O molecules for every 1 unit of barium hydroxide. If we wanted to name this compound, we'll call it barium hydroxide, just as we normally would. And then it is a hydrate, and we're going to use our prefixes we already know. So 8 is octa. So it's barium hydroxide octahydrate. Now, the other kind of permutation or form of this question you might see is rather than being told the exact masses, you may have to use some experimental data. So for my second example, we'll go through this one. Let's say we have lithium chloride and it's a hydrated sample. So I take the mass of this, place it on my balance, 5.235 grams. Now, similar to what you did with your copper sulfate very early on, we're going to put this perhaps over top of the Bunsen burner, and we're going to heat it. And when we heat it, we're going to drive off, or we're going to boil off the water. We're going to boil it until there's no water left. And we call it an anhydride, or it's anhydrous. After we've boiled off the water, the mass is 2.300 grams. So that is lithium chloride now without the water. From that information, from that experimental data, could you determine the formula of the hydrate and name the compound? So it's at this point, if you want to try it, you could pause and see if you could calculate moles of lithium chloride and moles of water on their own to help you find the formula. So pause it here, and then you're going to come back. And now you're back. So let's take a look at what we've done. We're told in the question, my lithium chloride, we need to find its formula. We'll use my crossover trick, LiCl. I had a mass of 2.300 after all the water had boiled off. I'm going to find the molar mass of a lithium and a chlorine, and here it is. And I'm just going to convert that mass into moles. Now I'm going to do the same thing for my water, but if you look at the question, look at the data you were given, you had the mass of the hydrate before, the mass of the anhydrous form. So the mass of water must have been the difference between the two. So that's after we have boiled it off. So I'm going to subtract those two values, and then I'm going to divide it by the molar mass of water. And here we have it. Now, if I want to know how much water there is for each mole of lithium chloride, I'm going to take those two values and divide the larger by the smaller, or in other words, the water by the lithium chloride, and I'm going to find there's about 3 times as much. Whenever you're doing these questions, you're pretty much, or should always find that you have the same or more water in moles. So it should always be the amount of water divided by the amount of the anhydrous form. So by comparing the amount of each, this is just a proportion. That's why the proportion is part of the unit. I find that I have 1 lithium chloride, move the dot back up, and there's 3 times as much water. If I had to name the compound, it's lithium chloride, that's LiCl, and then trihydrate, so 3, and then the hydrate tells me there's 3 waters. Okay, so that's the last one. This is really, in effect, this is just kind of like an extension of an empirical formula. You're finding the amount in moles of each, and then you're comparing them to come up with the final formula. So I'd like you to try these. If you have any questions, please pop on the meet and let me know.